He's like, of course I did. Like, what do you mean, of course? It definitely was a better plan to have it in the middle of the quarter than at the end. That senior skip day at the end of the quarter, not a good plan. Okay, so I'm recording now. So let's go back over properties of logs. And we used to always like to call these in pre-calc the expanding properties. For sure we learned these in pre-calc. For sure, once we learned them, we never did anything with them, because to the point where the other pre-calc teachers are like, why the heck do we even learn these? And I'm like, you need them in calculus. And they're like, oh, okay. So we still talk about these expanding properties, but oftentimes you don't ever see, if you don't follow pre-calc with a calculus class, you never see anything to do with them. The condensing you use in pre-calc when you're solving equations. Expanding, we never kind of seem to use. Okay, so what do I mean with the expanding ones? Well, there's that property that says, hey, if I have the log of a product, and it doesn't even matter how many pieces the product has, how many factors, that lets me, says, hey, the log of a product you can rewrite as a sum of a whole bunch of logs. You guys remember that? A little bit from pre, you're like, yeah, maybe no. And a lot of these log properties kind of always seem like super mysterious, because you're just like, how can that possibly be true? But then I would think probably most pre-calc teachers do what I do, and they go, well, look, if I have the natural log of 2 times 5, and then I do natural log of 2 plus natural log of 5, it's like a miracle. Okay? And there's ways to prove why these work. It has to do with the properties of exponents. If we do this generically, there's some very nice proofs for why these properties work. They're something we can use. We really don't have a reason in pre-calc to use this very much, other than it's good for evaluating sometimes. It's good for evaluating without a calculator, but it's also going to be really good for us for derivatives. So products, we took a product into a sum. And it doesn't matter if it's a regular log, a common log, a log base 5, a natural log, whatever. It's the same property regardless. Just the log you have on the left and the logs you use on the right have to be the same logs. So products turned into sums, and quotients turn into differences. And like I said, most of the time in pre-calc, you're asked to do this on a quiz. You're like, hey, expand this. And you never really talk about why you would want to. You just kind of do it. And you're like, look, I made it bigger. Great. Expand it, make it have more logs in it. Natural log of x divided by y is the natural log of x minus natural log of y. Quotients can become differences. Products become sums. And then the third one, you don't ever like think about this one as something different, and then maybe once you learn calculus, you're like, think this is related. It's this one. It's if you have the log of something like that, which you're like, I don't know what you would do with that, but basically the log of something to a power. That's not the property. The root x equals x to the 1/2. We know that. Do you remember what the trick is? the log of something to a power. What can you do with the power? It's just like, it's almost just like power rule in derivatives. It's, you do this. Once again, that's another one that you're kind of like, really? But then you try it and you're like, oh, let's see if we did, crap, where's my root? There it is. Natural log of root 5. Oh, it doesn't like that. Why doesn't it like that? Okay, I have no idea why it doesn't like that. Okay. Must be something in that side. Okay, so natural log of 5 to the 1/2. And if I have you do 1/2, natural log of 5, same thing. So I don't have a great phrase for this one. So how about, it's kind of more like something written with an exponent. The exponent becomes a coefficient. And we can have different mixtures of these. We can have products inside of quotients and powers inside of products, inside of quotients. And a lot of times that's what you practice in pre-calc. You kind of take something and you're like, okay, guys, let's take the natural log of AB squared divided by C and expand. Okay. So typically, when you learn this in pre-calc, bless you, you do products and quotients first, quotients before products. So that quotient becoming the difference, the product becoming the sum, and then the power coming down to the front. So you take something that looks like this, you're like, well, why do I want it to look like this? And in about a minute, I'm going to show you why. In pre-calc, we practice doing that in the logs and exponential unit. And we do a lot of go backwards, push things back together in equation solving. Because in equation solving, it's a lot better to have a single log expression than a bunch of them. But when we get to the point now where we're going to take a derivative of the log of something, the more complicated this something is, the harder it is going to be to write our derivative. It's going to be a lot easier to write our derivative of a bunch of little logs than the one log of a big scary expression. So that's what we're going to look at now. But at the forefront of this discussion has to be, we've got these rules, these tricks, these properties that allow us to expand. And so if we do have a product, a quotient, or something to a power, it's actually going to be in our best interest to expand it out before we take the derivative. Now, as ugly as this is going to feel, I'm going to show you that because we're going to do the problem. We're going to do a problem two ways. We're going to do it without expanding it first and struggle through it and get to the answer. And then I'm going to show you, hey, look, if we expand it first, if we rewrite it first, everything's going to be a lot smoother. Okay. You ready? Here we go. I want to take this function and I want to write the derivative of it. Oh, I don't want to write the derivative of it, but the long way. But I'm going to start. I might not finish it. I might wimp out. So let's talk about, you might be like, well, what's the big deal? You know, why is this going to be so hard? Well, let's think about it. I have the natural log of this big chunk of stuff. So my derivative is 1 over that big chunk of stuff. That part's not hard. Times, and I'm just going to write this in words, I want the derivative of that chunk of stuff. Now, in order to write the derivative of that chunk of stuff, that x times 2x minus 5 quantity all cubed, I would need to do a product rule on that, plus a little bit of chain rule on that set of parentheses. So if you don't want to write this down, you don't have to. I'm gonna write it down. I might do it a little fast for you, so just kind of, this is kind of just like watching the scary part of the movie. Just sit there and watch. That would have to be your next step. You're like, what? I took this. The derivative of this is, you probably can do it. You can follow it. You know, I have faith in you guys. I think you could follow it. That's the second chunk. The derivative of the x is 1, and then the x, and then the derivative of 2x minus 5 quantity cubed is 3, 2x minus 5 quantity squared times the derivative of the inside is 2. So it's all of this stuff times this. So I could have this guy over this guy, and then I could have all of this stuff. I can feel you guys like just pulling away from me, like, what in the world does she think she's doing? Like, that's what that derivative would look like. And if I held you responsible for cleaning it up, that would go there, and that would go here. Okay. I don't even want to write that down, okay? And I like this. Like, it's my career. And I'm still, like, right? That's an eye-rolling problem. Because this is so complicated that the amount of stuff you have to do to just do the derivative of this piece is a whole lot of calculus. That's a whole lot of calculus all by itself, plus putting it together with this thing, and then all the algebra you have to do. It's not impossible, because I wasn't about to do one that was impossible, or less, it was even messier, but it's straight up messy. It's straight up messy, and it's got a lot of pieces, and I would bet money I probably made a mistake. We'll find out, because when we do it the easier way, we'll see if we get this little pretty derivative. Okay, so that's the big scary way. Let's take the easy path. Or easier. We're going to use a trick that's going to help us. We're going to rewrite this function. I'm going to grab it. I'm going to grab it on the next page. Okay, oops. Okay. Let's go with plan B. Plan B says, I'm going to rewrite this thing using some log properties. I'm going to expand this out to a lot of little logs instead of the log of one big scary thing. So how about I write this as the natural log of x plus the natural log of 2x minus 5 cubed. That's just the product into a sum. Already feels better. And let's do one more step. Let's deal with that cubed guy. Let's throw that 3 down in the front. Okay. Oh, I think my derivative is right because I can already see it coming. You see that answer coming right now? Look at that natural log of x. When you take the derivative of that piece, that's the 1 over x. That's when this guy out here got multiplied by this guy here, and because I was distributing and then I cleaned it all up, that got me right there. All right, this back end, I'll keep my 3. 1 over 2x minus 5 times 2. I can, as long as that's not a product or a quotient or something to a power, it's pretty easy to take its extra derivative. I actually am like completely in love with this problem as an example. The reason I'm completely in love with this problem is I think it's an excellent illustration of exactly how the properties make everything nicer. If I know the properties, if I know the tricks of rewriting log stuff, then I don't have to go through cuckoo crazy world of 1 over this guy times the derivative of this guy, which is a whole lot of mess and nonsense, of chain rule with a product rule inside of it. Not that we can't do that, because I totally made you do that on a quiz in Unit 2, but, you know, nobody liked it. You know, it was hard. It's hard to get everything right when you're doing a product rule and a chain rule at the same time. And then, if I was holding you responsible for simplifying this down to an answer like this, well, you know, the fact that we foiled this to this, you know, I mean, a lot of you just would cry here. You're like, no, I don't even like you, Mrs. Willenbrock. I'm not doing that. But if we can actually get here, look how much prettier that is. It's so easy. Okay? It's so easy. If you watch for using a property. Now, that's going to be the catch. Are you going to be aware that you should use that properties would help you? That's part of what we have to practice, right? We got to do some problems, and some of them are properties would be helpful, and some of them the properties won't matter. If you use a property, as long as it wasn't illegal to use it, it's not bad. Let me show you an example of that. If you have something like this, pretty much, you know, I would just do that. So I got 3 over 3x or 1 over x. But technically, I could rewrite that as the natural log of 3 plus the natural log of x, because it's the natural log of 3 times x, and I can rewrite products as sums. And then when I take the derivative, the natural log of x gives me 1 over x. This is the part you might get upset by because we don't love like something like that. We're like, what's that? Well, that's just a number. It's like having a 7 there, or a 12, or a 55. You take the derivative of a constant, you get 0. So a property will work on this problem. It will help you. You can get to the answer if you rewrite this, but you don't have to as much as when this is a more complicated product or a quotient or you've got exponents in there. So you'll see some problems, I'll look at them, you'll be like, couldn't you have used a property? And I was like, yeah, but I just didn't. The thing that I really like to use a property on is the ones with the powers. Okay. Anything that where you have something here and it's also then raised to a power, that's a good indicator of maybe we would like to use the property. Okay. And put that power down in the front and then take that derivative. The property where the power, or the exponent becomes a coefficient. All right, so let's do one more where I'm going to say rewrite me first and then take the derivative. I'm going to give you the heads up. Okay, so rewrite, then find f prime. Okay, and here's what I'm going to give you. The natural log of 3x minus 5 over the square root of, oh, I don't want a 4 there. How about the square root of 6x? I like that. That's good. Find me the derivative of that. I strongly encourage you to rewrite it first. We got a quotient. And then you got a exponent that you might want to make into a coefficient. So remember here, natural log of a over b is the natural log of a minus the natural log of b. I am not going to do this problem the hard way because it's going to require a quotient rule. Ain't nobody want to do a quotient rule. I'm still jamming on the halftime show. quotient into the difference. Sums, product into sum, quotient into difference, you do first. And then deal with the powers. It's kind of like backwards order of operations. So ultimately, my rewrite on this would be looking a little bit like this. That's my f of x in a different life. The natural log of 3x minus 5 minus 1/2 the natural log of 6x. If you would like to write out natural log of 6 plus natural log of x, you can. Like I said, I hardly ever worry about rewriting if it's just a constant times an x. It just doesn't, I just don't look at it that way. This doesn't change. I know you're like, look at this and go, but it's a difference. You got to be careful. The log of, if it starts as a product, you can change it. If it starts as a quotient, you can change it. The log of a difference doesn't have, nothing happens to that. So here we go. Derivative. 1 over 3x minus 5 times 3 minus 1/2 1 over 6x times 6 so how about 3 over 3x minus 5 minus 1 over 2x. So here I'm still rewriting. This is me taking the derivative. Now, if I were going to, let me shrink this down for a second. If I were going to try to show that that was the exact same derivative, I would have to do I'd have to do 1 over this, and then I'd have to do a quotient rule of that. And to do a quotient rule of that, I would have to do a chain rule of that. I don't want to do that. Okay? Don't want to do that. So one of the ways, how can I prove? I like to prove that things are right. Let's see if we can prove this is right. I have an idea. 3x minus 5, 2x. I don't know if I can, I don't know how to do this on Desmos, but I know how to do it on the 84. Let's grab my 84 and do this and prove it. One of the ways you can prove that stuff is right is you can look and see if they would have the same value. So if I ask a calculator to do the value of this derivative, the value of the derivative of this function, and then I got the value of this function at a certain x, I should get the same answer. The derivative of the natural log of this function and the value of this function should be the exact same things. So where's my calculator? Calculator. Oops, that's not the one I want. Do I want to show this to you? I want you to know this. I'd be sorry, probably, but that's okay. Where are you? There you are. Okay. Oops. There you are again. So let's see. If let's make x be 1. So then if I typed in, actually not that, if I typed in, see how quick I can do this, 3 over 3x minus 5 minus I didn't mean to do that. I know, I left it blank. 1 over 2x. Okay, so the value of that derivative at 1 is -2. That's actually a very pretty answer. Okay, now here comes the tricky part, is I got to make the calculator tell me the derivative, the value of the derivative of the natural log of this without rewriting it. So this is going to be pretty messy. I'm going to do the derivative of the natural log of, now here's the thing, your calculator will give you derivative values. It won't give you derivatives in algebraic form. So I want the derivative of the natural log of this expression at 1. Please, Jesus, be -2. Oh, crap. Not good. What did I do? Oh, poop. Oh, but... Okay. Yeah, I didn't think enough about that. Crap. Always should test yourself before you do things. Yeah, it's gonna tell me this doesn't exist because this function actually doesn't exist at x equals 1, because at x equals 1, this would be negative, and you can't take the natural log of a negative. All right, so I just gotta pick something else for x. That was just a bad x to try. That was just a bad x to try. Okay, let's try a different x. Something that would the calculator, that function actually likes for x, because that function is not divided to 1. How about let me take a look at that original function for a second. Nope. How about it 2? Guys are like, I don't really care, Mrs. Willenbrock. I believe that it's right. Okay, I understand that. I have to verify that that's right, but I will verify it later. I'm pretty sure we didn't make any mistakes on that. So I'll verify that later. But 1 was not going to work because 1 doesn't work in this function. You can't have a derivative value for a function if the function doesn't exist. Natural logs are only defined for positive numbers. So when I put a 1 in here for x, 3 minus 5 is -2 over root 6. That's a negative number. This function is not defined there. So if we were going to graph this function, we wouldn't even see it, wouldn't even have a point at 1. So that was not a good choice. And I have it on video. Yay! Okay. Get to relive that moment. We'll have to edit that part back out. Okay. That's probably everything your brain can handle. Probably more than you really wanted to handle in one class. So let's check out what's going on in terms of your assignment. So page 291 is where the assignment is. I put this copy of notes here. I'm pretty sure we did something similar that day. After we went over the quiz review, we just sort of talked about the beginnings of logs. I don't know if we did any derivatives that day or not, but I don't know what we did, but I put a copy of what I did second period that day there. And I will put a copy of today's notes in here as well. So what you're going to see is on page 291, I'm actually asking you to do 11 problems, 1 through 6, 9, 10, 11, 13, and 17. Okay. I have this not as a turn-in spot, just to kind of have it. And once again, reminder, we are not on the skills warm-up, but under exercises. And if we check out these exercises, the first few are pretty straightforward, and then you start to get some twists and turns. So 1 through 4, pretty much hit those with your natural log rule. You should be in good shape. If you wanted to use a property on number 1, you could. If you wanted to use a property on number 2, you could. But you probably don't, you don't necessarily need it. The derivative of what's the argument of the natural log is not that hard to find. For 5 and 6, you're definitely going to want to use a property. Because you have the natural log of something raised to a power, it's going to be a whole lot easier if you rewrite that where the power is a coefficient and then you hit it with your natural log rule. 9 is a product rule that you cannot get out of. It's a product rule because it's not the natural log of a product. It's a natural log function inside of a product. So there's no rewriting on 9. It is going to be a product rule problem. And the same thing for number 10. 10 is going to be a quotient rule problem because it's not the natural log of a quotient. It's a natural log inside of a quotient. But 11 and 13 and 17 would all benefit from a rewrite first. So 5 and 6 and 11 and 13 and 17, I'm going to give you a heads up. Think about properties first and rewriting before you try to hit those with your derivatives. 1, 2, 3, 4, pretty straightforward. 9 and 10, product quotient rules. All right, so I've given you a lot of direction so that you can practice the skills. As we go forward in the unit, or in this little piece of unit, we will practice identifying when we need to do which things. We'll mix them up and kind of do that. We'll make sure we focus on that so by the time quiz time rolls around, we have gotten good at that, knowing when to hit it with a property, when it's just a product rule, when it's just a quotient rule, when it's just kind of do the natural log rule. Okay, that's your assignment. 1 to 6. 1 to 6, 9, 10, 11, 13, and 17. Having that ready for class on Thursday would be a good plan so that you're practicing, so you're building your skills, not waiting until the night before the quiz to figure out what's going on. Okay. All right, I am going to stop this goofy video.